Thank you for that overview. John's going to join us for discussion afterward, and I'm going to tell you a little bit about what happened, kind of starting a little bit in the time frame that he discussed there, but really about the nuts and bolts of testing and drafting of the code, and then a little bit about the implementation, which is fresh, but it's happening. But like I said, my name is Anthony Dente. I'm a licensed civil engineer in the state of California, number 80,715. And I'm the vice president of the Cobb Research Institute. I also own Verdant Structural Engineers in Berkeley, California. I'm in Berkeley, California right now, and the sun is just rising. So I appreciate you all hanging with us late in the afternoon and be spending my morning with me. At Verdant, we've designed over 100 natural building projects: Adobe, Cobb, Rammed Earth, Earthbag, etc. Lots of straw bale. We have a 10-person team, which I couldn't do without my two business partners, Kelsey Holmes Foster and Kevin Donahue. Kevin Donahue was one of the 3 members task force that drafted the now adopted for a number of years now straw bale code in the United States. He was an integral part of the straw bale research that happened in our country in the early 90s and early aughts. And I moved out here about 12 years ago to practice under him. And we've been building a lot of buildings, designing a lot of buildings. And, I mention all those types. We do everything from residential to medium commercial. To be a good natural builder engineer, you need to fully understand all conventional building types and materials. The foundations, the roof systems aren't changing much just because we might have a clay wall system necessarily. We'll talk more about that. But why do we care about Cobb? I find Cobb to be fascinating because it's the lowest common denominator of a greater discussion here. We have this rainbow, this bridge. This is diagram is here for fun. It can't be completely accurate. But when you start at the lowest common denominator, you have a lot of directions you can go. We have this matrix of very fundamental materials, and you'll see some of the ways we've been able to develop it and utilize and implement it thus far. Now, I should say I'm a structural engineer. Again, thank you all for having us out. Unfortunately, the virus, I suppose, curtailed my all expenses paid trip to see your country for the first time. But I look forward to coming one day and maybe be able to shake your hands or even I can't even think about giving a hug right now. It seems like such a foreign idea. But I want to say that I know that you all don't live in a seismically active country. I am going to be mentioning some seismic information, and you might say, why do I care? I consider that anytime that an earthen building, a Cobb building falls down in an earthquake and actually hurts someone is bad for all of us. And it's bad for the material long term. And that's why it's important. But I'm not going to try to stick on that information too long. Just tell you what's interesting about our process and move on. I'm going to be talking a bit about steel reinforcement. And I want you to know that, we always try to shoot for the most natural, low carbon system in the first place. But we always attempt to not be idealist, not kill a project because there's some simple steps with a slightly non-natural material. You'll see we have some very engineered, very steel dense options. I'm not saying or recommending that people use those. I'm just saying that, if you want to have small walls in high seismic zones, you do have options to still use clay wall systems. And that's why they're there, not to tell people that we want them to not be using, straw only wall systems. But just the future needs to be diverse and have as many options as possible with as low a carbon as possible. That's my feeling. And I respect anyone else who's got a different opinion on that. I know that the opinions range wide, and I can't see your faces, your grimaces, or anything now. So I'll just assume that that was received fine. I have this, we all have great respect for the folks down in New Zealand. We try to take small steps that can make big changes. This report that came out of the observations of the Christchurch earthquake, it showed, in particular, there weren't many cob buildings in that report, but there were a few, and they didn't perform very well, partially because it is important to concentrate on different forms of reinforcing, but it's also important to have like good foundation systems, good anchorage to decent diaphragms above, preferably lightweight roofs. These houses that were documented here, and a lot of the illegal houses being built in the backwoods, I know in the Western United States, tend to not have all the details that just simple details, easy details, connection to roof top plate that can really take load path and make it happen. And so, we're trying to get those into the lexicon, into the cob building world, so that next time there's a report done in an area that had a lot of cob buildings, we might be able to see a little bit more just isolated. How did the cob work? Not maybe what happens to a wall when it's not anchored to its roof or has a kind of questionable foundation system underneath it. Back, I'm going to run through some designs, design and small scale testing from 2012 to 2018. Let's start permitting some of these buildings. What do we need to do to get these through? Let's learn the kind of questions that the building department's going to ask. And so we have a loophole in our code that's called the Alternative Materials and Methods chapter, which states that the code does not prohibit the use of any material that meets the intent of the building code. But that's rather broad, but it's a good open door. So then you have to kind of take testing and any other documents you can find. At the time, we had the ASTM standard E2392 started by David Eisenberg and backed up by Bruce King, both colleagues, mentors of mine. He did that in 2010. That's ASTM standards, not necessarily adopted in the ICC codes, but it is an ASTM standard. And then it references that engineers should use the New Zealand standard. So we go to the Alternative Materials chapter. We then say, here's an ASTM standard that's not in the code. And the ASTM standard says that we should use the New Zealand code. And so, here's until we get to a design, taking advantage of the straw bale code that was adopted but not implemented at that time. And then we started looking through at existing testing and engaging with small scale testing of our own. And one of my big takeaways was that anyone engaging in any scale of testing on any kind of natural building material, log all your variables. A lot of these, I show the Saxon report, 1995, Plymouth University on the left. That was great for me to find at the time that I did. And I'm not speaking towards that report specifically. I just noticed that it was there. I wanted to bring it to your attention since I'm talking in the UK and Ireland here. The types of clays, the quantity of clay, the quantity of all the material in the mix. So often one report will document this, another report will document that, but very few existing reports right now document all of them. And we don't know what kind of effect fully that clay volume are really having on these materials. You'll see that right now we just took every single test we could find, small scale, based remotely on cob, and we put them next to each other. And there's quite a broad range of outcomes for just bending and compressive strength. Modulus of elasticity is even broader. And as we focus in and try to find why is this, we need to be able to see the whole picture. So if you know anyone testing, always really encourage to get as deep into those details as possible. Then we got into a few permitted designs. Like I said, we wanted to hear how the building departments responded. In 2012, I started my first permitted cob design. And the, the politics, our goal was to win this one through endurance. It took us nearly 3 years to get a permit on that building, though it was right next to the Hayward Fault in Berkeley, California, which is the major fault in the East Bay, not that far away from the San Andreas Fault in San Francisco. So very real loads, seismic force is relative to weight. This is a heavy building material, and it's, it could be dangerous if it cracks off in the wrong way. And so it's important to pay attention to. We have respect for that process, deep respect. And the compromises in the end of that project were that they mandated that we use the exact same reinforcing steel, minimum reinforcing steel for the masonry code, and that the project is technically not habitable. You'll see a photo of that in the bottom middle of my screen. But and then there's another project John shared with you, the Shasta Hot Spring, where we got away from the horizontal solid bar into the meshes. In this project, we explored a basalt mesh actually to attempt to have a little less corrosion concern. And then from those experiences, we realized we needed to do some more testing of our own. What testing was needed primarily for this US-based code to just get our first foot in the door, thermal and earthquake, in plane and out of plane. Earthquake also relates to wind, but Cobb, because earthquake force relates to weight, it's always going to be harder for a mass wall system to resist earthquake forces than it is wind forces. So normally Cobb, Adobe, rammed earth, they do decent in wind and significantly less decent in earthquake forces. But the testing complications, as we started cracking this egg open, first is obvious cost. Private labs, private funding of student research is expensive, but genuine interest from student faculty is not, though it has other, real inputs needed. A lot of people have been doing partial scale models or half scale, and there's elements that don't scale up. When you want the full picture, the full kind of failure mechanism, you need to test at least some full size. And labor intensive and drying time and location. I have this quote at the bottom of, and then weight, when you build a 7 foot by 7 foot by 1 to 1.5 feet, I know you all work in metrics units. I'm sorry, but you're going to have to deal with the English today. You might end up with something that weighs 5,000 pounds or plus, and that's larger than most standard forklifts that we have here in our country. So do you bring the cobbers to the lab, or do you bring the lab to the cobbers? And that's a question I'll get more into, the complications of how we kept realizing what a complication that was again and again and again. I'm sharing because I want everyone to not have to start at ground zero. We all want to be building on top of each other. But the thermal testing, I don't know if any of you have ever been to Fresno, California. It's a beautiful place. Air quality is not that great all the time, but John and I took a long trip with a bunch of very heavy Cobb samples in a van. And I dropped them and John off there in, I think it was late 2018. And because we needed official R value numbers in order to begin to draft this code. And what we found, I learned at that time as a structural engineer, I often leave a lot of things up to an architect and focus pretty much on the structure. And I realized that at that point, in fact, I had some correspondences with some of the great builders in Ireland about your struggles with thermal. At the time, I did not know about the cabbage at the time. And I was starting to realize how under-addressed this was. And that it obviously, it still needs a lot of attention. I'm so grateful that the cabbage folks and you all are spending the time and intention on it. We're watching very closely and excitedly, and we're doing a lot of bale wrapping as well around here. I think the verdict's still out where how far and what the best all the good ideas, what are they all going to be in the future? And we found out that we had 0.22 per inch. It wasn't that great. This was a pretty dense mix, actually, that we took down there. It was about 110 pounds per cubic foot. And everyone thought, well, what if we make it lighter? Maybe it'll get better. But we kind of highlighted that, we know the insulation value of straw bale. We know the insulation value of lighter, more dense, light straw clay. And, here's this density chart. It's all in a line. So it's there aren't going to be any major surprises, and we just need a significant approach change, such as cabage, such as bale wrapping, and other kind of ideas that are coming forth right now. We're excited to see, but some full-scale wall testing we embarked on. I'll explain right now, and it's the first of its kind as far as we know, and to have full-scale in-plane and out-of-plane load testing done on cob walls. And we learned a lot from the Getty Institute and the South American research going on with Adobe's, so we're well aware and of that testing and tried to stand on the shoulders of that, taking it farther with the monolithic matrix of cob. Some things worked, some things didn't work. And again, it seems like such a disaster when you only have one test when something goes wrong. But we're doing this one test because we want a lot more tests to happen after it. And we just hope that people will, that we can help them not make the same mistakes. It took a lot of collaboration. My company, Santa Clara University, we were tied in through the straw bale research and Oasis Designs down in Southern California, Quail Springs Permaculture, north of LA. Wonderful place, great builders, a lot of natural buildings down there, and Cal Poly University in San Luis Obispo. And, it took a lot of conversations, a lot of collaborations, but, we made it happen. And I'll show you the photos here, but I want to say first about some problematic vocabulary that I want to talk about this so that you understand why I'm saying what I'm saying as we go forward. Just quickly, I think as a building community that we could do, it's not these terms aren't necessarily inaccurate, but I don't think they're helping us. And stabilized earth, clay materials with cementitious or asphalt binder added, and then unstabilized earth is the clay materials that don't have that. And it almost seems like you took out the stability, but really you added something. And unstabilized earth, it sounds like it's inherently unstable. And it's hard to get away from these terms because they're actually quite embedded. A lot of literature refers to them, especially when you get into that not that great, but few engineering documents. But I think we'd be better off calling it a clay mix and then like a stabilized clay mix. That might not be the right answer. I encourage you all to develop your own ideas, and as a community, we can come together with what the right one is. Another thing, unreinforced adobe. In seismic zones, a very bad thing. Unreinforced masonry, no one recommends it. It can be a dangerous material. That being said, a monolithic cob wall containing straw reinforcement is not unreinforced. It might be under-reinforced for the application, but there have been plenty of tests done that document increased ductility by the addition of straw in a cob mix, meaning that it is a tensile reinforcing in a compression-based material. So the International Building Code, the US-based engineered code, does not specify the requirement for what makes a reinforced system. And it also specifically references microfiber reinforcement in concrete mixes. So the groundwork is laid, the precedent is there for this type of reinforcing, and I think it's important that we acknowledge it. We went down to present to the students, cost. We're trying to engage students that are already doing research at Santa Clara. Massey Burke, a longtime collaborator, brilliant designer, researcher, builder, and Martin Hammer, who was the lead author of the code that we developed. And I decided to wear my Abraham Lincoln beard that day in case the cob and clay materials weren't scaring the students enough. Here I'll highlight the complications of building cob in labs. And there may be many researchers watching that know all this, but at Santa Clara, we took the cob to the university and we brought in experts to help the students build. And, we had to leave these buildings here for, over 3 months in their labs. other things going on. And, in the bottom, we had to do these funny splices because there was some miscommunication about the all threads that we had intended for the lower aspect ratio walls. When you're using student labor, that's sometimes it's more likely to have that. On the right here, you'll see Desiree and Julia, the two master's students at Cal Poly that ended up taking the research equipment to Quail Springs. They took the lab to the Cobb Builders. And up on the top, you'll see the view from the out the door of the room that they let me stay in at Quail Springs. And on the left top, you'll see the where we were staging the clay at Santa Clara. Pretty different environments. Like I said, I mentioned the splicing. There were some other things that we had to buy a new forklift, or not. We had to rent an upgraded forklift at Santa Clara, but at Quail Springs, they had a malfunction of the load actuator on the first wall, and so we got decent failure mechanism observations, but we didn't get great data. Whereas at Santa Clara, we were able to use the machine that was fully intact. Pros and cons both ways. To be honest, I don't know which I would do, which one I would pick next. But that's our experience there. And it's loading. We're going to the next page, but I believe the next page is highlighting on maybe a little bit more about the complications. And oh no, I'm talking about reinforcing in Cobb. When you step beyond straw only, there's solid bar, such as conventional concrete, but then there's meshes, and we explored a vertical and horizontal solid bar. We explored horizontal mesh systems, and then we explored vertical mesh systems. And the vertical mesh systems were more with Cal Poly. And then there was one design with Cal Poly. I don't want it to distract your attention, where they were using a repurposed drill stem steel, recycled post-industrial steel members. To just see how strong they could make it. It reached incredible strength, but it ultimately was over reinforced, which is not a good thing for seismic design, because it could snap and have a catastrophic failure immediately. But that was a kind of a sidestep to a radical idea by the author of that. The lead author of that test. But I want to highlight, for the straw only wall systems, we found that we found a failure mechanism called rocking shear. This was suggested by some of the professors at Santa Clara University, and it's when a wall is able to lift off the ground and support its own weight, so that it can use its own weight to resolve that force. When you have a really heavy wall that therefore has a really high seismic force, and you can use that weight to also resist that seismic force, this is a big deal. Almost none of the researchers expected the straw-only wall system to perform like this. We were calling it the common practice wall, where we just made some undulations in the foundation system. You can see the photo in the bottom left. And so it was left unanchored, and the rocking shear is a practice that's done a pretty high level engineering, very larger buildings, a lot of engineering focus. So bringing it to a residential level, a very small scale level, is something that's not done very often. But the potential of using cross walls, buttresses, to increase the uplift resistance of these wall systems, we don't know the full scale of that yet. I'm excited to find out. We tested these generally 1-to-1 aspect ratios, but how far do you go that, I can go back and show you, you can see how it lifted off the ground. How wide can these walls be that they will still lift off the ground with only straw reinforcing? That's yet to be told, and I'm excited to find out the limits of that through testing. And we've been running numbers and have our estimates, but it's important to find out for real. We tested skinnier aspect ratios. Everybody's wants to know how thin can the walls get, how small, how many windows can we get. It's on the south side, we got to get more windows, and that's in conflict when you're in an earthquake country with a heavy wall system. And But that's where we used. We were more liberal with our steel use in these walls. You can see there's more bending action when you get into smaller aspect ratios. Again, I'm loading, and I believe that the following slides talk about the double mesh. And there was one wall, and it's the 661010 double-sided mesh performed incredibly well. And it had two vertical mesh planes of 661010 kind of slab reinforcing mesh. It performed at 2.3 times its self-weight, and just really stood out as, in order to build that cob, you've got to reach in between those 6-inch wide holes to place the cob. It's not an easy method. A lot of people don't want it. But if you're in a position that you need extreme force from a wall, you have the option here, and it is doable. So that's good to know. We did some out-of-plane testing. I learned a lot about the waterbed industry, which we used as the bladder to apply the force to the wall. If you have a chance to support the waterbed industry right now, I highly recommend it. They're having a hard time out there. That's my wife showing the structural integrity of the waterbed. But we placed the waterbed between a very robust wood wall and inflated it until failure. And when there was a minor vertical reinforcing in the center of the wall, we easily got to seismic design category D loading with an appropriate factor of safety. And that was big news. We did find that for the 13-inch thickness and 7-foot wall height that we used, that the straw-only wall system was, from this test, appropriately applied to seismic design categories A and B only. And so there's caveats within that. You can work with that, thicker wall systems, but simply adding a little bit of steel will or vertical reinforcement of some kind can get you take you a long ways. Other structural information worth noting. We talk a lot about curves. Our building's curved, so everything's okay, right? And I always say, like, only sort of, kind of. We like to emphasize that a pipe is very strong, but when you cut a front door and a back door and a pipe, it becomes two half circles, which are still strong, but not as strong as the pipe. And it's important to remember that. We got this into the code, first step into the code as much as we could. Mesh reinforcing is a fine idea. I recommend not being afraid of it if it's especially horizontal mesh. You just lay it down, you keep cobbing up above. When using straw reinforced only in areas that have any kind of seismic force, it's important to pay close attention. This is actually the hardest to make work. And it's the most complex. Don't think of it as the easiest or the, it's the most dynamic and should have the most attention paid. And we often found that failure for in-plane and out-of-plane tests happens at the cold joints, no matter how much attention was paid. I had some of what I consider the best cobbers in our country building these walls, and they were like, it was definitely wet when we got out there the next day. But it's obvious it's going to be the failure point. It's going to be the weakest point. It's hard to deny that. So maybe we just accept that and move on until someone proves us wrong. But it just seems to show up at every single test. So the residential code appendix, like I said, the IRC is the US-based prescriptive code. We found that the IBC, International Building Code, is the US-based engineering code. And the lead author was Martin Hammer, who's also the lead author of the straw bale, the light straw clay, and the tiny homes, lead or contributing author. I should clarify, I'm not sure exactly which role he played on each of those codes. Though, talking about politics and relationships, we often hear that, just because cob buildings are hard to build legally in our country does not mean that they're illegal. We found that the relationships that have started to be developed through the straw bale code, the light straw clay code, benefited us tremendously. A structural engineer named Kelly Cobean, who was there on behalf of FEMA, our disaster program here in the United States, she stood up and testified with us. And it was, I don't know if we could have done it without her. Her openness to review our plans and speak in confidence with us to the board. David Eisenberg was a significant contributor, and there were a lot of things, unique code drafting that, there's a lot of prescriptive codes, not a lot, but there's a number of them, and of them in Europe and in other areas. New Zealand's got their prescriptive code, but there's just certain things that we needed to address, particularly structurally, that we felt like it was the first time we were kind of putting that language on paper. And when you have to commit to the paper, it brings a new gravity to the situation. We learned a lot about things we might not have been fully addressing. You kind of had to take a hard look at your designs in this. And here's a number of figures we put in the code. As you'll see in the bottom middle, we're addressing code. We're giving, because of the section modulus upgrade, we're giving more advantage to shear walls and out-of-plane loading when you have tight enough curves to apply. Anchorage to your roof diaphragms. On the bottom left is a gable end wall. Topics that, if not engineered and focused on, that hinge point there can be quite dangerous if you're designing your building like that. The top left, upper left document shows how, again, addressing curves, addressing the concept of horizontal meshes, vertical bars, if you're in that seismic zone, and roof attachments and tapered wall systems. And the scope of the code, it had its limitations. We had to limit it to, we didn't have to, we chose to limit it to seismic design categories A, B, and C based on the current research. More research is needed. Seismic design category D steps up into a higher level of needed engineering attention. But you'll see our wall types A through E. We start with A, which is that common practice wall. No anchorage to the foundation. We have anchorage to the bond beam. There's no vertical steel and there's no horizontal steel. And so it was important to everyone that we got the common practice wall into the code, and we're proud that it's there. Like I said, I think it has a lot of potential for rocking shear development over time and learning about that system. But thermal performance, as we said, the cob, and as the dense cob mixes that we're used to in the kind of thicknesses that have become common, it's not cutting it for the current R value requirements in at least in the International Residential Code and the California Residential Code. There is option for additional insulation here, AU 109.3, which kicks you back to make sure you're meeting the permeability requirements of AU 104.1. But as it stands, if you would simply build, a modest cob wall thickness without additional insulation, your climate zones would be limited in the United States with this code. The process of the ICC hearings, we found, I found to be quite accessible. Anyone can show up, anyone can propose a new addition to the building code. You get 2 minutes to talk in front of the board. They're very strict about it. Then there's rebuttals that go back and forth. Ultimately, people in the room can stand up and come and talk on your behalf or talk or speak against your proposal. Ultimately, we failed the first round because of we were claiming a 1 hour fire rating, which was an incredibly low bar for a material that we make fired clay pots out of. We're basing that off of research from some from New Zealand and other areas of the globe. Also, just some preliminary non-official tests, which I have a photo of on the right-hand side here, that were done. You know, we would expect that this material has somewhere between 4 and 8 hour fire rating, and realistically. They praised our work structurally on a heavy mass wall system, and they failed us because of fire, which was a very interesting experience. We removed the fire rating, and we went back to the second round, our only other chance to pass the code, in Las Vegas in October. And I was very surprised that clay building was the thing that took me to Las Vegas. I had to miss the second half of Earth USA in New Mexico, a wonderful conference there if you ever have an opportunity to attend. And we turned out to be successful. And the Las Vegas hearings are different than the first hearings. They're made up of building officials from around the country. We had a number of people that we did not expect stand up and speak on our behalf, particularly about fire, about this non-combustible material and the need for it in our changing climate in the globe. This is going to be in the 2021 IRC, which if California is the 2022 CBC, and it'll be law in January in California 2023. It's a long process. They play the long game. I want to note that we are still a bit in debt from doing all this. I volunteered all my time as the lead engineer on the project. That we had a lot of other expenses. If you know anyone who's interested in helping out, we have a donate button on our cobcode.org page. Happy to talk at length about many other additional research topics that I strongly recommend. We're trying to make connections all across our country and across the globe. People that have genuinely interested students and faculty, we can easily shoot them over. You know, here's the precedent set already for this test, and here's what we recommend you do. But not in we need to be in control of it. You take it from there. But we can. We have that information, and we can shoot it over. You have anyone interested in these types of topics? I know you all have your own researchers that are doing great work in all kinds of topics that I'm not hitting on. So believe me, we have tremendous respect for the research you all have been putting in. I thank you for it. Quickly. We already heard of a permit in North Carolina that was, under design at the time that the Cobb Code was approved, and that helped them kick over their permit process into being a legal building. John mentioned the fire rebuild plans that CRI is developing, and there's many designs underway. At Verdant Structural Engineers, currently we have 6 Cobb buildings being designed, 3 earth bag buildings, 5 adobe, at least 15 straw bale, and more. You know, all these systems, they're so related, but they're so different. Yeah, you want to talk about them at the same time, but you also want to keep them isolated. Mesh reinforcements, clay strengths, foundation attachments, insulation value of the materials. But yet one's block, one's monolithic, and one's taking its structure through its plaster and one's taking it through its body. At Verdant Structural Engineers, I just like to end presentations with this, that, we want to take this bigger. I have a strong passion in getting carbon-based, carbon storing, hopefully agricultural byproducts into bigger buildings. We're working on a number of pursuits in that realm. If you got anybody in the States or anywhere that's interested in help on that realm, please contact us. Thank you. Let's stay in touch. I really appreciate you having us out.